Hi, my name is Jared Hedrick, and today I'll be presenting my enzyme lab poster. I did this project with Armand Mashasha and Stephen Kirshner. Today we're going to be talking about biological catalysts, more specifically enzymes. So what an enzyme does is it lowers the activation energy of a given reaction, so that way you can put the same amount of energy into the reaction but get more products, which is good for all reactions occurring. And more specifically, our enzyme uses hydrolysis, which is the process of taking water to split the peptide bonds out of proteins to get more. And more specifically, we're going to be talking about trypsin today, which is the enzyme that we worked with inside of this lab. So trypsin does break down the proteins using the hydrolysis method. The role of it is to break down the proteins in our digestive system so they're much easier for us to digest. Trypsin in all animals is located in the small intestine, and that's good for it because it's slightly alkaline with about a pH of 8, and it's a perfect pH for it to live in and produce or break down the proteins inside of it. Um, and our question that we had today was how can we affect trypsin and what affects trypsin? So we had groups look at temperature, pH, and salinity, and for our specific lab poster, we are doing ours about salinity. So the question we had was, does salinity affect the rate at which trypsin functions? And our hypothesis was that if salinity increases inside the environment with trypsin, that means the function of trypsin, the rate of it will decrease. So higher salinity levels, the worse trypsin is going to work. So for our experiment that we actually did is we took 7 centrifuge tubes and we filled those all with 450 microliters of different reaction buffers. So those were our salinity levels, and those ranged from 0 to 4.8. The specifics were 0, 0.3, 0.6, 0.9, 1.2, 2.4, and 4.8, all of those being molar respectively. And then after that, we added about 500 microliters of azocasein. And what azocasein is going to do for us is it's going to break down, it's going to be the protein that trypsin is going to break down within the experiment. So that will measure how effectively trypsin works in each of these buffers. After the azocasein, we added 50 microliters of our trypsin. So that, as soon as we add the trypsin, is going to immediately start to react with the azocasein and start to break it down. So as soon as we do that, we are going to put it in our incubator, which we have set at 38.6 degrees Celsius for 20 minutes. We chose 38.6 degrees Celsius from another group. Their range is about what temperature that trypsin worked in perfectly. They found that 38.6 was a very good environment for it to work in. So we actually took theirs, so that way we can have an accurate result, and we know that temperature isn't going to be a factor about whether or not the trypsin actually produced, and just our salinity. So after incubating for 38.6 degrees Celsius for about 20 minutes, we took it out of the incubator and we added 10 microliters of TCA. And what TCA does for us in this project is it stops the reaction between the azocasein and the trypsin, which is good. So now we have the 20-minute window of the 38.6 degrees Celsius incubate time, and we know that the amount at which trypsin broke down azocasein isn't being affected by more time than less time when we start to read it and before we centrifuge it. So after we took these out and put the TCA in, we centrifuged it on max speed for 2 minutes. What the centrifuge does is it pulls down all the pellets that we don't need to read for the spectrophotometer. So it actually takes the supernatant on top and the substrate on the bottom. So that way we can just pick apart the supernatant, because the substrate on the bottom is the result, is what the bacteria and the trypsin actually secretes, and we don't need to read that. We just need to read the absorbance level for the spectrophotometer of the supernatant. So we draw out the supernatant and we put those in spectrophotometer tubes, and then we read those at a specific absorbance level of 450 nanometers. We do it at 440 nanometers. We do this at 440 nanometers because that is the pigment in which it's be able to absorb. And then after we do that, we take the absorbances and we put them into our data set. Now, before we get into our data set, I want to talk about our negative control group. Our negative control group was set up with all of the regular experiment going on, except we did not add any trypsin. So with no trypsin, there should be no reaction whatsoever, and we shouldn't get any absorbance levels, or rather a very low absorbance level. If, in fact, there was some kind of absorbance level that was anywhere near the amount that there was for trypsin, we know that something has been contaminated, or that trypsin isn't the one actually affecting the absorbance rate. So we did 3 trials of these. We did 3 trials of them to make sure we had a good data set, so that if one was off, we could justify it by getting rid of it. And we did those at 3 different reaction buffers just to see if it was actually the reaction buffers that actually made it react or not. We did that at 0, 0.6, and 4.8. And we did kind of the 2 radicals of 0 and 4.8, and then we did a good 0.6 that if anything was going to react, we know would react there. Going back to our example, I forgot to say this, we actually did that 4 times. We did it 4 times because we felt that 2 times isn't enough, that if one data set is off, we can't tell which one is which. If we did 3, if one of the data sets was off or 2 of them were off, we wouldn't be able to expel them and get accurate averages. So 4 is a good median ground, considering if you have 4 trials that all work successfully, you have a great set for your data. And if you even have one that isn't accurate, or 2, you still have enough to say which one should be which. So, looking at our results, we have our hypothesis was shown to be correct. At 0 molarity for the salinity, you can see that the average for the group was the highest absorbance rating, and that for 4.8 it was the lowest. In the middle, it kind of peaks. It starts at the very top and then it goes down a little bit, and then it goes up again, and then it kind of plateaus off onto as soon as it starts to increase dramatically to the 2.4 and the 4.8 salinity. All of our t-tests came out below our p-value, so we know that means that they were accurate, they were good. We don't have to worry about whether our test results weren't too different or too variant. For our negative controls, we see that there was little to no absorbance, so we know that the trypsin did affect what was going on when it came to the absorbance reading, and we know that our positive controls were good. And same with our negative control t-tests; those were extremely low, way below their p-values, so we know that in fact those were also accurate measurements. So our hypothesis was supported by the data. However, we want to take it a step forward, and instead of saying a general trend, we want to make sure that we set a specific point about which one is going to be the most accurate. We could reset our experiment to a closer range, that range from the 0 to about the 1.2, because we know everything after that isn't going to affect how salinity, we know it isn't going up, so we want to make sure we hit that range where it was going up and then back down, so that we can find the most accurate result for that. We could try to improve it by also adding more trials. The more trials you do, the better averages you'll have and the more accurate results you could have. If we had the ability to reuse this trial with other groups, we could try to find a more specific pH or temperature range. However, unfortunately, we're not able to do that at this moment, but if we could, we would take the results from other groups and then compare them to our own. And that is my enzyme lab.